Differential equations, we're still in section 2.5, now in day 3. We have really been going through different types of differential equations. We've seen the separable differential equations. In fact, you saw that in BC. We saw the linear, where we went ahead and we found integrating factors. We had the exact, the almost exact, where we multiplied by an integrating factor. Homogeneous, we just did Bernoulli. Today we're going to get reduction through substitution to create a separable differential equation. So here's what you'll see. You might see a function where it sure looks like you have an inner composition, and we're going to make a substitution with u. We're going to find a du dx. We're going to do that substitution, and then we'll be able to separate, which will allow us to solve quickly. We'll solve for u, and then we finally resubstitute. So let's take a look at such an example. As you're looking at example 1, dy dx equals 1 minus x minus y all over x plus y. It wouldn't take you too long for kids to say, wow, if I factor out a negative, I'd have 1 minus the quantity x plus y. And at that point, what we can really make note of is, wow, that's the same exact expression, so we could go ahead and get u equals x plus y. Let's go ahead and make a substitution where we're going to be able to do that. So if you see a nice reoccurring pattern there, or sometimes it just shows up once, it's clearly something that you can substitute, go ahead and do that. And then find your du dx. Well, du dx, we're going to take our derivative with respect to x. The derivative of x is just a 1. And then we have a dy dx. Tell you what, I'm going to solve for dy dx. You might think, well, why are you doing that? Well, as we substitute, of course, we're going to be able to now come over here and make this left side du dx minus 1. That's what we just saw that's equal to. On the right side, this becomes 1 minus u all over a u. And this is looking better already. If we just did a little simplifying, do a little I heart math right here, this becomes 1 over u minus u over u, which of course is just a 1 itself, isn't it? So you'll have 1 over u minus a 1, and pardon me, in my haste, I didn't quite copy the left-hand side correctly, did I? We've got that minus 1, and we can add a 1 to both sides. And now what? You can see, my goodness, this really is separable. So tell you what, I'm going to simultaneously multiply both sides by a u, and also multiply by dx. And hey, would you look at that? Right now you've got your separable differential equation. This will become u squared over 2 would equal x plus a c. And it's at this point where our u was x plus y. We could plug that back in. And guys, that's it. We'll have our final answer written out this way. It's solved implicitly. Could you actually go ahead and try to solve for y by taking square roots? Well, I suppose you could. This is good enough. The next example, I'm going to be very honest with you, can be a lot more difficult, not involving the substitution per se, but just the amount of work that might have to take place as you solve through and have to do some old integrating, and sometimes these problems get a little ugly. Notice it's an initial value problem. You have y of 0 equals 0, and I would venture a guess that most people would quickly, look right here at example 2 and say, well, my word, right now, I most certainly would believe that a nice substitution that we could make would be that u would equal negative 2x plus y. And indeed, it would. And remember what we did next. We'd take a derivative. We'd get du dx would equal, well, this would just be a negative 2 plus a dy dx. We're taking a derivative with respect to x here. And then you solve for dy dx. Because honestly, if you're going to start substituting, and if you'd like to change this problem, what you're about to do is really take this dy dx, this whole expression right here, and your left-hand side is going to become a du dx plus 2, and then over here on the right, we would have a u squared with that substitution. Remember, that's the whole purpose for doing this. And we'd have a u squared minus 7. Now, at this point, it probably does not look very strange whatsoever. You can subtract a 2 from both sides. And, yeah, you've got a separable differential equation. You can real quickly divide right over here. But you're about to see, guys, that as we integrate, it's the integration in particular that's going to get rather messy right here. And, as we try to integrate, this is not arctangent, 1 over u squared minus 9. That would have been 1 over u squared plus 9. I am going to do a little bit of review here just to help you out. The 1 over u squared minus 9 is really 1 over u plus 3, u minus 3, and we're going to do a partial fraction decomposition. Now, of course, the TI-89 could come to our assistance, but it certainly would be a good review right now to go over this and to talk through it. And you might remember we could let u equal certain values, like we could let u equal 3, and this a expression would disappear, and 3 plus 3 is 6, we'd get 6b, so b would equal 1/6. We could also let u equal negative 3. And if we let u equal negative 3, well, now this other part of this decomposition is going to disappear. We'd have negative 6a is equal to 1, so a would equal negative 1 over 6. So we have a negative 1 over 6 and a positive 1 over 6 right here. So, continuing on, on this left side, this integral would become negative 1/6 times 1 over u plus 3 and a positive 1/6 times a 1 over u minus 3. So, and by the way, the right side just becomes x plus c as you take an antiderivative. But then you might remember that this would be a negative 1/6 natural log of u plus 3, and this would be a 1/6 natural log of u minus 3. And my goodness, right now, we could multiply everything by 6. I think that could help out substantially. And you could have a 6x. Well, 6 times a constant is just going to get you a c anyway. And then what? These fractions disappear, and you'd have an ln of u minus 3 minus the ln of u plus 3. We could do a property of logs and real quickly just get this going right here. And then what? Well, we can exponentiate. We can go e to both sides. And pardon me, this is a plus c. By the way, when you go e to this 6x plus c. That's like e to the 6x times e to the c. And e to the c is just some constant. I could call it c2, or we could even call it just a c all the same. But what are we really left with? Well, my goodness, as you're working through this, we could even drop our absolute value here. We can talk about why, because whether our absolute value would be plus or minus, that constant is still going to be a constant, isn't it? And right here, my goodness, as we're just plowing through this, you could resubstitute in for u if you wanted to, but I think it's easier to solve for u right now. Because if you can solve for u, if you could get u alone, then you can very easily solve for y in another step. So tell you what, I'm just going to real quickly do some cross multiplying. And as we multiply through here, we'd get, c2 e to the 6x times a u plus a 3 c2 e to the 6x. And tell you what, I'm going to bring this term over and I'm going to bring that term over there. And we'd subtract, we'd get c2 e to the 6xu, and then we'd have a 3 plus 3 c2 e to the 6x. And tell you what, I'm going to factor out a u. That's kind of nice. You can see, and by the way, you could also factor out a 3 if you'd like to. That's kind of easy, isn't it? And, at this point, then you can quickly divide and nicely, very nicely, get an answer for u. Now, the thing is, u, as you might have seen earlier, was really negative 2x plus y. So we really have negative 2x plus y is equal to 3 times 1 plus the c2. And by the way, you could even just drop the subscript. You could just call it a c altogether. But solving for y then, you add a 2x, and you've got this right here. Now, there's only one other little catch that I do want to bring up. We've solved for y. Here's the last part. It's an initial value problem, isn't it? And this initial value problem was 0, 0. So, when we plug in a 0, 0, your y is 0, your x is 0. Let's see here. E to a 0 power. E to the 0 power is just going to be a 1, isn't it? And down here, it's going to be much the same thing. E to the 0 power is just going to be a 1. So while we're getting there, we're really super close. You can see this and this is just a 0. And then how do we solve for C2? Well, it's hopefully not going to be too much work. You can cross multiply. And as you do that, you're going to see that you get 0 is equal to 3 times 1 plus C2. You can divide by a 3. And you get 0 is equal to 1 plus C2. C2 is negative 1. So what you do is you come back up here, and wherever you had a C2, you just turn it into a negative 1. And, 1 minus a negative 1 turns into a plus. And we're done.